Good morning, everybody. This is Dr. Jingbo Louise Liu from the Department of Chemistry, Texas A&M University, Kingsville. Today, we are going to discuss experiment number 2, determination of Reed law. So the objectives for this lab, to determine the Reed law for a chemical reaction. Number 1, you are going to determine the Reed constant for a reaction. Number 2, you are going to determine the reaction order for the reactant. So particularly, we are going to choose one of them. The second objective related to utilize a graphical analysis of your experimental data. You are going to draw a best fit straight line. You are going to derive a slope from the straight line or based on the best fit straight line. And then you are going to determine the activation energy for the particular chemical reaction. So based on your observation, so what you are going to find, you are going to find the temperature change, concentration change of your reaction or reactant per unit minute. You are going to observe the volume of gas produced per time unit. And then you're possibly going to take a look of the color change per time unit. So that's what you are going to essentially discussing. Regarding the chemical reactions, there are several factors is going to affect on the reaction under a specific set of conditions. Every reaction has its own characteristic rate. Therefore, so this nature of different reactant is going to determine the chemical reaction. 5 factors can control the chemical reaction. You can control these factors to determine the reaction rate. The first one called the concentration, second one physical state, third one temperature, fourth one the utilization of catalyst. The very last but not least, the specific surface area. For example, if you have an imaginary reaction, A2 plus 2 moles of B2 produce 2 moles of AB2. So that's what you are going to produce. How do you determine the initial, we call the initial reaction rate? The reaction rate for this particular reaction equals K times A to the power P times to the B2 to the power Q. So this K is your reaction rate constant. K is your rate constant. This rate constant relates to the rate of your reaction to your initial concentration of the reactants. And this K is also going to vary with the temperature, and this one is independent into the reactant concentrations. Your P and Q, they are called the reaction order for A, for molecule A2 and the molecule B2 respectively. In our lab, you are going to work on this reaction. Under oxidizing agent hydrogen peroxide, your potassium iodide will be oxidized to iodine, I2, and your hydrogen peroxide reduced to water, which is liquid. In this case, you are going to control the pH value at a constant number. Therefore, this reaction rate, K equals to the I2 to the power P to the hydrogen peroxide to power Q to hydronium to power R. This hydronium is constant. You can simplify your reaction rate law to the K prime to the I negative to power P, hydrogen peroxide to the power Q. What you are going to do, you are going to determine the K, or you can say K prime, and P and Q. K, so we are going to show you how to determine it by controlling the different concentrations. You change the concentration of I negative potassium iodide, and you fix your hydrogen peroxide or vice versa. So here is what you are going to do. For example, using nitrogen monoxide reacted with oxygen, you produce nitrogen dioxide. So in your experiment 1, 2, 3, 4, 5, you are going to change oxygen reactant, nitrogen monoxide reactant. So you change the concentration. How do you change it? My suggestion is fix the one concentration, such as nitrogen monoxide is the same for your experiment 1 and 2, two different trials. You double, you do 2 folds, 3 folds, you double the concentration of your oxygen molecule. Similarly, you control the oxygen concentration the same, such as your number 1, 3. You double your concentration for nitrogen monoxide. Also, you can triple the different concentrations. In this case, you can determine the different reaction. We call the reaction initial rate. And then you are going to do this calculation. You are going to use the reaction rate 2 and 1. You use reaction rate 2 and 1. You assume your rate equals K times to the oxygen to the power 2 times the concentration of nitrogen monoxide to power N. Because you control nitrogen monoxide at a constant value, therefore, constant can be crossed out. Your K, as long as the temperature stays the same, K is also the same value. Therefore, you are going to cross out the same quantities. You simplify this rate 2 over rate 1, rate 2 over rate 1. Simplified, K also can be crossed out. So therefore, you have your concentration for your number 212 of oxygen divided by concentration of oxygen for your number 112. So you have this number. So this is 2 times of the first one. Therefore, so you are going to replace the numbers into your equation. So you have your rate for 2 different concentrations, and you have your concentration which you prepared. So you have your, my calculation is 2 equals to 2 to the power m. 2 equals to 2 to the power m. Your m can be determined, which is 1. Meaning this oxygen is undergoing the first order reaction. Similarly, you can reuse your reaction trial number 1 and number 3. So you are going to do the same calculation. My calculation for your nitrogen monoxide reaction order N, this N, my calculation turns out to be number 2. Therefore, you are going to determine the reaction orders. How do you determine the K? The K, you are going to apply a logarithm, either log, L-O-G or L-N, ln. And then what you are going to do, you are going to receive a straight line. You are going to do the best fit line, and then you figure out y equals a plus bx. Similarly, you are going to apply the reaction, apply logarithm onto your reaction rate law. Rate equals k to the reactant to the power p. You assume the second chemical is constant. You make this approximation, simplify it, and then you apply the logarithm. You get log rate equals log k plus p times log a. You apply logarithm of your rate, as a function of logarithm of your concentration. Concentration is what you controlled. Log rate is what you determined. Therefore, you are going to obtain a straight line. You are going to do the best fit. So you figured out your slope. You have your slope. Slope represents your P is your reaction order. Your log K, logarithm of K is your y-intercept. From there, you can determine K. That's another way for you to determine reaction rate, constant K, and also you can determine the reaction rate order for the different reactants. So we also can do it as what I showed you how to do it. How about the activation energy? We already knew activation energy is related to K based on Arrhenius equation. The Arrhenius equation is shown in this equation. In this K equals A, which is a constant value, is called the correlation frequency factor. And then you have your A times E to the power activation energy over RT. If you have two different temperatures, so you can calculate two different K values. And from there, you can determine the activation energy by applying this graph. You are going to plot a graph using logarithm of K or ln K, take logarithm ln K over 1 divided by T. You use your reciprocal of absolute temperature as your X. K Kelvin is the temperature unit. And also you apply best fit line. Figure out the slope. Slope equals negative EA divided by R. Your y-intercept equals your ln A. From there, you can determine the constant value A, and also you can determine your activation energy EA. This R is called ideal gas constant, which is 8.314 joules per mole per Kelvin. So that's how you are going to determine the activation energy. Followed by, I did give you several examples on how you are going to do the calculations. I will leave these different calculations for our students to finish by yourself. Another method, another important point I want to show you is called iodometry. Iodometry is a reducing agent is used to titrate directly with iodine to produce iodide. You have your I2. If you allow I2 to be reduced, you are going to produce iodide. If you have your iodide in excess, you are going to titrate this. You are going to titrate this excess iodide with something we call the thiosulfate, S2O3 2 negative. This is a reactant which you are want to back titration, to do the back titration. From the color change, you can determine the end of your titration. And then you can do the calculation based on the moles. So about this color change, we are going to use a very important chemical called starch. You dissolve your starch or disperse your starch in water. That starch composed of two major molecules. So I showed this in your two graphs. That starch is going to be reacted with your iodide. Actually, I should say triiodide, because this I negative doesn't really exist. You are going to produce I2 and I negative as a triiodine. This triiodine is going to be bonded through the covalent bonding with your triiodine, I negative. So you are going to see a very dark blue complex. You produce a complex. This complex gives you a very deep blue, meaning your reaction length is going to be determined from the time you count your time to the time you observe the deep blue. So that's how you are going to stop your reaction. So also another point I want to mention is about the H2O2, your hydrogen peroxide. In this lab, make sure you use deionized water. Otherwise, your hydrogen peroxide is going to be decomposed to water and oxygen molecule. You are not going to have your oxidizing agent. Sometimes students showed me our reaction never turns blue. The reason is you don't have this reactant in your chemical reaction. So another one, you are going to use a buffer solution. You use a buffer solution, sodium acetate and acetic acid. In this case, you control the concentration of sodium acetate and acetic acetate. You control it. You make your concentration of hydronium constant. Therefore, you simplify your reaction rate law. So I also listed about 7 different important questions. Answer those questions. They will enhance your core knowledge, will also give you an outline an outline, a framework about what you are going to do in this lab. And also I listed several tables for you to particularly controlling the different concentrations. So you can control your initial concentration. So the stock solution we gave you one, you are going to do the dilution. You take a certain amount of your concentrated iodide, you dilute it to say 10 milliliter, 20 milliliter, etc., etc. If you have 0.3 mole per liter of your iodide, you take 1 milliliter, dilute it further to 10. Similarly, for your hydrogen peroxide, you are going to do this dilution. Again, so you need the accurate concentration of potassium iodide and accurate concentration of your hydrogen peroxide. And also, we are going to use thiosulfate, potassium ions. So your potassium thiosulfate solution, all of this solution, accurate concentration must be known, it must be prepared. And then I give you a second table to show the determination of your rate and rate constant. Make sure you recorded your new initial concentration. You control that. You did this different dilution. And then you are going to determine the time of your color change. Imagine you have a timer, determine the color change, and then you can calculate your rate. Regarding the rate loss, this slide showed you 3 different types of rate loss. The first one is called, oh, I made a mistake. This is the zeroth order. For some reason I said third. Sorry for this. This must be the zeroth order. The very last one is the zeroth order. The first plot is called first order. First order chemical reaction rate law is a lean concentration of A at any time equals negative KT plus ln A initial. This A is the concentration of your reactant initially, and then this T is the time. Now you apply the logarithm, so you are going to also receive a straight line, best fit straight line. The slope is negative K, and your concentration initial, you take a logarithm, so that is your y-intercept. Similarly, you can determine the second order. Second order, you are going to use 1 divided by concentration of your A at any time equals KT plus 1 over A initial. The very last one, sorry again, this is supposed to be the zero order. The zero order equals the zero order rate law expressed as the concentration of your A at any time equals negative KT plus A0. This is initial. Also from the slope, from the y-intercept, you can determine K and you can calculate the concentration initial. So I also gave you lots of different integrated rate law expression and their related units. So units for your K. For the different orders, for 0, first, second, third order, they have different units. This table will be very handy, very useful for you. And then this table even more useful, I'm going to consider. I summarized the 0th order, first order, and a simple second order reaction about what's the rate law expression, what's the unit for K, what's the integrated rate law. Integrated rate law meaning you consider the concentration and the time. Your rate law, you only consider the concentration. And then how do you determine K? So how do you plot a graph? So to get a straight line, so give you Y and X, and also what's the meaning for your slope and y-intercept. Also, how do you calculate the half-life? Up to this point, I'm going to conclude my lecture for today. So you have a beautiful day. Stay safe and stay healthy. Again, thank you so much for listening.